In this presentation, we consider parallel resonance for an AC circuit. So for a parallel circuit, it's actually easiest to analyze the resonant circuit if we use a constant current source instead of a constant voltage source. So in our parallel circuit here, we have a constant current source, and then we have a resistor, a capacitor, and an inductor, which are in parallel with one another. And these types of circuits are often used in communication equipment, such as AM/FM stereos and television transmitters and receivers. They often will have a very high resonance frequency and also have a high quality factor. So let's start by considering what this circuit looks like and when resonance would occur. So the first thing that we have to realize is that in general, inductors have some resistance associated with them, and that resistance of the coil cannot be ignored. A circuit like this is often called an LC tank circuit, and in that case we have to reanalyze this in such a way that we take the inductor, the pure inductance of the coil, which is in series essentially with the resistance of the coil. So everything that's in blue here represents my actual inductor, and we model that actual inductor as having some inductance in series with resistance. And so what we need to do is we need to convert that into an equivalent parallel circuit so that we can analyze this as everything being strictly in parallel. So my goal would be then to take this inductor, this real inductor, and convert it into having a parallel resistance and an inductive component. So if we recall back to earlier discussions, we can take an equivalent impedance in parallel that has a resistive piece and has a reactive piece, and we can convert that into a resistive piece in parallel with a reactive piece. And so without going back through the derivations, because we did some of that before, we can determine how these parallel pieces can be found by using the series pieces. So when we do that, what we find is that the equivalent parallel resistance for that particular inductor depends on the resistance of the coil of the inductor squared plus the reactance of the inductor squared over the resistance of the coil. And the equivalent reactance of that inductor depends on the same quantity at the top, but the inductance of the, the reactance of the inductor. So RP is only the resistance that's parallel from the coil, and then the X here is the reactance, the inductive reactance, and that depends on the angular frequency times the inductance. So I can rewrite the expression for the reactance, the equivalent reactance, in terms of the resistance of the coil and then the angular frequency times the inductance squared over the angular frequency times the inductance. So why do I care about writing it this way? I care because of the fact that at resonance, all of the impedance in the circuit is resistive impedance. And so the reactive components for the capacitor and for the inductor actually cancel each other out. So those two reactances must be equal to one another, where now this is just the purely inductive piece with no resistance associated with it. So if I set the inductive or the capacitive reactance with equal to the inductive reactance, I know the capacitive reactance is 1 over the angular frequency times the capacitance, and now I have this equivalent reactance for the inductor, which depends on the coil resistance and the actual pure inductance part and the angular frequency. I can rearrange terms a little bit, and if I multiply both sides by the angular frequency times the inductance, it cancels out the angular frequency, and then I have the inductance over the capacitance equals the coil resistance squared plus the angular frequency times the inductance squared, and I can solve for what that resonance frequency is. So remember, resonance occurs when the capacitive reactance is equal to the inductive reactance, and that only occurs for a particular frequency based on what that coil resistance is and the inductance and the capacitance. So the parallel resonance is just the square root of 1 over the inductance times the capacitance minus the coil resistance squared over the inductance squared. If I factor out 1 over the inductance times the capacitance, I get that the parallel resonance frequency is 1 over the square root of the inductance times the capacitance. This first term becomes a 1, and then I have this, I factored out an L and a C. So anyway, I get the coil, 1 minus the coil resistance squared over the ratio of the inductance to the capacitance. And you might wonder, well, why do you care about doing that? The reason that we care about doing that is because there's some special cases. So when that coil resistance squared is much, much less than the inductance over the capacitance, the square root is approximately equal to 1. So if I look at the term here that's under the square root, right here, I have 1 minus the coil resistance squared over the inductance, the ratio of the inductance to the capacitance. So if this resistance squared is much, much less than the inductance over the capacitance, then this whole square root is 1, and essentially the parallel resonance frequency is just 1 over the square root of the inductance times the capacitance. And that is actually exactly the same as it was for series resonance. So that's kind of nice if that occurs. So essentially the assumption here is that we can use is that if the inductance over the capacitance is greater than or equal to 100 times that coil resistance, then to a good approximation we can say that the resonance frequency for parallel resonance is 1 over the square root of the inductance times the capacitance. So let's consider what the current is through the different components at resonance. So I want to be clear here in my picture that this is purely inductance right here. Okay, so there is no resistance of a coil for this inductor. In my picture, any resistance that was present has been combined with this total resistance here in parallel so that I have pure resistance, pure capacitance, and pure inductance. So everything that we did earlier is still valid, just keeping in mind that the coil resistance has already been combined if there is any coil resistance. So the first thing we realize is that the inductor and the capacitor reactance cancel each other at resonance, right? So whatever the reactance was for the capacitor and the inductor, if we are at resonance, those two reactance values cancel each other out. And so the impedance in our circuit all comes from the resistive piece. And so that means that the current through the resistor is just the current from the load, because the current comes in here and essentially all of it will pass through this resistor because that's all of the impedance. Yes, there can be current in these other components, but they are always canceling each other out in opposite directions. So one would be positive and one would be negative. Because these components are in parallel, I can figure out what the voltage is across any one of those components because I know the current that's going through the resistor is just the current of the source. So in my particular picture here, this would be just the current times the resistance with a phase angle of 0 because my current had a phase angle of 0. If I want to know what the current is through the capacitor, it would just be the voltage over the impedance of the capacitor. These really should be bolded because I am using phasor notation. The voltage is just the current times the resistance, phase angle of 0, the value that I found above, and then the capacitive impedance is just the capacitive reactance with a phase angle of -90. 0 minus a -90 is a positive 90. So the current through the capacitor is just the ratio of the resistance in the circuit to the capacitive reactance times whatever the current is from the source with a phase angle of 90. And I can do the same thing for the inductor. Again, these are all phasors. So the voltage across the inductor over the impedance of the inductor. The voltage across the inductor is the same because everything is in parallel. The inductive reactance, or the impedance of the inductor is the inductive reactance phase angle of positive 90. So when I subtract them, when I get the current, it's a negative 90. This is the resistance over the reactance times the current of the source. And the thing I realize is that these two currents are exactly the same value in terms of their magnitudes because their reactances are the same. So they have the same current, but they are out of phase with one another by 180 degrees. So even though there's a constant current source here and that current is going through the resistor, there is still current through the other components. It's just that those currents, if you use Kirchhoff's current law, they would cancel each other out. We can also talk about the quality factor for a parallel resonant circuit, and the reactive power, the quality factor is just the reactive power over the average power. So remember, reactive power is the power from either one of the components, the capacitor or the inductor. It's not both because combined together the total is actually 0, but the quality factor is just taking one of those reactive powers and dividing by the actual average power from the resistor. And we can write this in terms of the inductor or the capacitor. So the quality factor for parallel, since the voltage is staying the same across all the components, we can use the formula for reactive power, which would be the voltage squared over the reactance. And then divide that by the actual power of the resistor, which would be the voltage squared over the resistance. Because of these fractions, the resistance comes up to the top and the reactance is on the bottom. And of course, the reactance here can be capacitive or it can be inductive. So the quality factor can be written as the resistance over the reactance of the components. So you'll have a high quality factor for parallel if the resistance in the circuit is large compared to the reactance. The quality factor is often bigger than 1, and so what that quality factor is also related to is how the currents through the capacitor and the inductor, the magnitude of those currents compare to the source. So I can write down that quality factor as the resistance over the reactance. And then if I use the equivalent of Ohm's law, I actually flipped this around a little bit. So this is equivalent to the voltage over the reactance. So I multiplied the top and the bottom of this by the voltage. All right, so both top and bottom are multiplied by voltage. And then I separated them out. So I would have voltage over reactance, and that's on the top. And then on the bottom, I would have voltage over the resistance. This is a fraction, so remember it can be brought back up to the top. If you don't like this, which I can see where algebraically it looks a little weird, you can come up to this expression right here for the quality factor and just cancel out one of those voltages, right? Voltage over reactance, voltage over resistance. It's the same thing here. And I know that according to Ohm's law, the voltage over the reactance is just the current through that reactive component, and the voltage over the resistance is the actual current through the resistor. So I can rearrange this, and I see that the current, the magnitude of the current through the reactive component is just that quality factor for parallel times the current. So for example, if you had a quality factor in your parallel circuit that was 10, that would mean that the current through the inductor, the magnitude of the current through the inductor and the capacitor would be 10 times the actual current of the source. So this is similar to the series resonant circuit, and the quality factor actually told us something about what was happening to the voltage across those components instead of the current. So for a series circuit, if you had a high quality factor, the voltage across the reactive components was larger than the source by whatever that quality factor is. And so for parallel circuits, the quality factor is telling us how much larger the current is compared to the source. We can examine the impedance of a parallel resonant circuit, and we can think about what's going on at resonance, but also at frequencies that are not at resonance, but above the resonance frequency and below the resonance frequency. So in general, I can write down the total impedance, or not the total impedance. I can write down 1 over the total impedance in my circuit by adding all of the impedance values as the reciprocal. So I have a resistor in the circuit, I have a capacitor in the circuit, and I have an inductor. And so I can add all of their impedance values together. And so if I do a little bit of my complex division, I have something that has a real part, and then I have the two reactive components that have imaginary parts. If I convert that into rectangular form, I get that 1 over the total impedance is 1 over the resistive piece plus 1 over the capacitive piece minus 1 over the reactive piece, and that's in the imaginary part, right? So this would end up giving me an imaginary positive real number and imaginary negative real number. So using this, I can put those terms that are the imaginary parts over a common denominator, and I get the inductive reactance minus the capacitive reactance over the multiplication of those two quantities. And then I have a complex number that has a real part and an imaginary part, so I can determine the amplitude, or the magnitude of that complex number, by using the square root of the real part squared plus the imaginary part squared. And then after I get this expression, if I wanted to know what is the actual impedance in the circuit, the magnitude of the impedance, I could take the reciprocal of this, and that would tell me the actual impedance in the circuit. So I take this value and I take the reciprocal, and I get this expression. And so at resonance, the impedance in my circuit is the largest it can possibly be. And so what happens is the capacitive reactance and the inductive reactance at resonance are equal to one another. And so this whole term is just 0. And so I get something that is 1 over the smallest number in the denominator that's possible, and therefore I get the largest impedance. And so that's where I'm at right here. At resonance, when these reactive components are equal, I get the largest impedance in my overall impedance in my circuit, because remember, it's a parallel circuit. So now we're interested in looking at what happens when the frequency increases beyond the resonance frequency, and then also what happens when it's below the resonance frequency. So I keep in mind that the capacitive reactance is 1 over the angular frequency times the capacitance, and the inductive reactance is the angular frequency times the inductance. So if the I have to really think through this. So if the angular frequency is large, so if it's very large, then that means that 1 over this large number, the capacitive reactance is small and the inductive reactance is big. And if the angular frequency is small, then 1 over a small number is big, and then the inductive reactance would be small. All right, so let's think about what happens to this quantity here, which is the inductive reactance minus the capacitive reactance over the summation of these two quantities. So if my angular frequency is very large, I'm up in this range right here, then that means that the capacitive reactance will be, I said that backwards, the inductive reactance, this quantity, will be much larger than the capacitive reactance. So for all practical purposes in this expression, for very large angular frequencies, this number is significantly bigger than the capacitive reactance, and so I can ignore that piece, and I could write this as just the inductive reactance over the combination of those two inductance values, and as I look at this, the inductive reactance cancels out. And so the only thing that's really important then is the capacitive reactance. And so in terms of higher frequencies, it's the capacitive impedance that actually dominates. And thinking about it in the opposite way, if the frequency is low, that means that this value is a small number, that fraction is large. The capacitive reactance is actually much bigger than the inductive reactance. And so when I subtract those two quantities, if the capacitive reactance is very large, then essentially it's more important here. So I could ignore the inductive reactance and I get the expression I have over here, but I realized that I would cancel out those two capacitive reactants and the only thing that's left is inductive reactance. So the inductive impedance is what dominates essentially the importance in a parallel circuit for frequencies that are lower than the parallel resonance frequency. In the same regard, I could look at what happens in terms of the angles. And so realistically, we probably don't even have to write all this out, because what we learned is that, from the previous example, is that if you are lower frequencies, that means that inductive impedance dominates, and inductive impedance has a positive phase angle. And if you have higher frequencies, that means that the capacitive inductance or impedance dominates, and that has negative angles. And so this kind of a curve sort of makes sense. We could just figure out what the angle is. So in general, if I wanted to figure out the angle for this particular complex number, which is 1 over the impedance, I would take the inverse tangent of the imaginary piece over the real piece. So there's the imaginary piece and there's the real piece. I can multiply the top and the bottom by the resistance, and I can bring this term down. I get this term right here. I can plug in that the inductive reactance is angular frequency times inductance. I can do the same thing for capacitance. It's 1 over the angular frequency times the capacitance. I can do a little bit of factoring. Of course, in the bottom, same reasoning as before, those terms, the angular frequency cancels because one depends on the angular frequency, one depends on 1 over. I can pull out 1 over the angular frequency times the capacitance here. And I can do a little bit more manipulating, and I end up getting that the angle for this particular complex number, which is 1 over the impedance value, is the inverse tangent of the angular frequency squared times the inductance capacitance minus 1 over the angular frequency times the inductance over the resistance. Lots of terms here. I realized that if I actually wanted to know what the angle for the impedance is, it's just negative the angle of 1 over the impedance, because remember, the difference here, if I take 1 over the impedance, I would have an angle here of 0, and it would basically just change the sign of my angle, and in terms of tangent, that just changes the sign of the term that's up front. So if I wanted to know in general for a parallel circuit, what is the angle for the impedance, I could take the inverse tangent of this expression right here. And that sort of allows us to see what is dominating in our expression, but also the previous example also goes through that. So what we're interested in is also determining what the half-power frequencies are and the bandwidth for our parallel circuit. And so we know that the half-power frequencies tell us when the power is half of the maximum value. The maximum power occurs at resonance when the two impedance values for the capacitor and the inductor cancel each other out, and the resistor gets all of the current from the source. So the maximum power is just the current from the source squared times the resistance. We'd like to compare that to the power at a different instant in time at a different frequency. Not so much different instant in time, I guess, a different frequency. So this occurs at resonance, but in general we can write the power through that resistor at any frequency as the voltage squared over the resistance, where all of these terms have exactly the same voltage because they are in parallel. And we can determine what that voltage is by figuring out the equivalent impedance of all of these three components together that has some total equivalent impedance. And we can figure out the voltage. It would just be the current of the source, this current times that total equivalent impedance. So the voltage squared is the current squared that's coming out of the source times the total impedance, at a particular frequency divided by the resistance. So we're interested in when is this power half of the maximum power? So we can plug in our values for the actual power and the maximum power, and we realize that the currents that are given here are both the currents of the source, and so they cancel each other out. And I also can cross multiply and bring my total equivalent resistance to the other side, and total equivalent impedance to the other side, and I can bring my resistance over. And the reason for doing that is because I have an expression for 1 over the impedance, the total equivalent impedance squared. And that was, we looked at that in the previous slide. And so we have 1 is equal to 1/2 the resistance squared times 1 over the total equivalent impedance squared at any given frequency. And of course, I realize now that I have resistance squared and then I have a 1 over resistance squared, so I can factor some things through. So I've done quite a lot of algebra here, right? So I've multiplied both sides by 2, so that's where this 2 comes from. And then I have factored this resistance through the expression. So the r squared times 1 over r squared gives me a 1, and then r squared times everything else is right here. And I've also plugged in that my inductive reactance is angular frequency times inductance, and my capacitive reactance is 1 over the angular frequency times the capacitance. This 1 subtracts off from the 2, and I can take the square root of both sides, and when I take the square root, the left side becomes plus or minus 1, and then I have my resistance, and then I have the terms that I took the square root. I can do a little bit of rearranging, and I can move that L over C to the other side along with the R, and then I have this expression here. I can multiply both sides of the equation by angular frequency times capacitance, and I get this expression. And then I can rewrite it in terms of putting everything on one side of the equation. I have a term that depends on the angular frequency squared times the inductance and the capacitance. When I move this term to the other side, it becomes minus plus the inductance over the resistance times the angular frequency, and then minus 1. I realize that I need to solve this using the quadratic formula. And I can plug in, this looks like a squared x plus, it looks like 0 is equal to ax squared plus bx plus c. And so when I use the quadratic formula, I get this expression here. And of course, I have plus minus and another plus minus, so this gives me 4 angular frequencies. Only 2 of those values are positive. So once I combine these terms, it becomes a positive. I can do some rearranging again, the LC and the L over R here and the 2, and I realize that the term under the square root is always greater than the term that's out front, which means that this has to be a positive, and then the other terms can be a plus and a minus. And so I find that the lower half power frequency is just equal to negative 1 over twice the resistance times the capacitance plus the square root of 1 over 4L squared C squared plus 1 over LC. And then the upper half power frequency looks very similar, except for the fact that it's a positive up front. So I realized that these are half power frequencies in terms of angular frequency. If I wanted to calculate them in terms of actual frequency, I realized that the angular frequency is 2 pi times the frequency, so I would have to take that number and divide by 2 pi in order to get it in terms of hertz. So these these expressions are in terms of radians per second. The bandwidth is just the difference between the upper half power frequency and the lower half power frequency. If I take the difference between these two, I get 1 over RC. Because the square root terms are going to cancel and the terms out front are the same, they just have a factor of a half in front of them. This would be the answer in terms of radians per second. If I wanted to know what the answer was in terms of hertz, I would have to divide that answer by 2 pi. I can also write the bandwidth in terms of the quality factor, similar to what we did before. So if I multiply the top and the bottom by the resonance frequency for parallel, I realize that the term on the bottom here becomes 1 over the resonance frequency times the capacitive is the capacitive reactance. So I have capacitive reactance over resistance times the parallel angular frequency. If I take the inverse of that, that's the quality factor. So the bandwidth can also be written as the resonance frequency over the quality factor, and this would again be in units of radians per second. So we have a way of determining what the maximum power is at resonance. This says series resonance should be parallel, and then what those half power frequencies are.